we were looking at the limits of finite sums. So remember, to get a more accurate area, we're going to consider the width of each of these rectangles. So we started with 2 rectangles, each having a width of 1/2. Then we had 4 rectangles, each having a width of 1/4. And then ultimately, if you kept this pattern going, you would have n rectangles, each having a width of 1/n. So what we want to do is let n go to infinity, because then we would have infinite many rectangles, each with the width that is more or less trivially small, that there will be no over or underestimation, just because it's going to be so close to the actual curve. So we have this set up for us that the area is the limit as n approaches infinity of f of 1/n times 1/n, f of the 2/n, which gives us the height of the second rectangle, times its width 1/n. So we wrote this using our summation notation, our sigma notation, as f of k/n, because if you notice, it's the numerator that is advancing in terms of the index, which is going to be k. And then the width is just, of course, could be kind of, you could think about it as just, it's going to be 1/n in each scenario. So this is where we left off last time, and maybe just to clarify where this step came from, notice that our function given to us is f of x is equal to 1 minus x squared. That's the curve we're looking for the area under. So you can see here's this 1 minus x squared, except for instead of x, we're evaluating it k/n. Does anyone have any questions out to this point right here? So that catches us back up. So this is where it gets a little bit more algebraic, a little bit more mechanical. So let's go ahead and see how this plays out. I'm going to probably need to write a little bit smaller because we have about 4 steps we need to fit in here. So we're going to still bring down the limit as n goes to infinity. And if you look at what we're going to do next, is we're going to just go ahead and distribute this 1/n through. So we're going to have the sum, as k goes from 1 to n, of 1/n minus k squared over n cubed after we go ahead and handle the distribution. And again, maybe just to clarify, I'm going to go ahead and add some parentheses right here to say this is the single formula for the summation. And again, we talked about some ways, some properties last time to go ahead and work with summation. That is to say, each of those 2 terms we can sum separately, just kind of using the commutative property. So again, the limit as n goes to infinity, we'll evaluate that later. The next step is just looking at this separately. I'm going to go ahead and, instead of writing another step, so you can imagine that we're going to consider this summation with the 1/n, and then we're also going to consider the summation with this second part right here. So if you remember that there's no index in this first part, does anyone remember what we can do if the indice is, there's no index with that part of the formula? We could just multiply. So we multiply 1/n by, do you remember? Yeah, the ending index, in this case, n. So this first one is just going to be n times 1/n. And then the difference will come down. And then we have the constant value rule. That is to say, here, let me do this in red to match what you did above. The 1/n cubed comes out in front, but we still have the sum from k equal 1 to n of k squared. So again, that n cubed is fixed for each of the terms in the summation if you were to expand that. So you could just factor that out. And then we have this sum from k equal 1 to n of k squared. The good part about that last summation is we have a formula for that up above. So again, just here for reference, what we're going to do with this last term is use this formula that was provided up here. Again, you do not need to memorize this, but so it is provided. But just to see that we can take this summation, the sum of the first n squares, and replace it with this formula that is based entirely off the ending index. So let's go ahead and do that on the next step. So we still have the limit as n goes to infinity of, let's see, that's first part is 1 minus 1 over n cubed. And then we're going to multiply this by that formula, which is n times n plus 1 times 2n plus 1, all of that divided by 6. So maybe just for some reference here for what we're doing, this step right here we had on page 235 in the workbook, and these were rules 4. Then we also used rule 3. And this one right here is we got above on page 236, where we're looking at the sum of squares. K equal 1 to n is going to have a formula. So just maybe for reference, what we did in each step over there in gray. Any questions so far? Okay, so we're pretty much there at this point. We could just go ahead and maybe just write things a little bit differently to make it more obvious. The limit as n goes to infinity of 1 minus, and if you were to go ahead and FOIL this out, you'll end up in the numerator with a 2n cubed plus 3n squared plus n, and that is all going to be divided by 6n cubed, just working with the fractions. I just FOILed out and carried some algebra. Then we're almost there. Remember, so we can take the limit. So remember the limit of a constant. So the limit of 1 is simply 1. And then does anyone remember what the limit of this term that I've circled in red would be? As n goes to infinity, we have the horizontal asymptotes. So remember, you look at the degree of the numerator and the denominator. If they match, like they do here, that is to say they both are of degree 3, what did we look at to find the limit of what is circled? Anyone remember? The leading coefficients. Yeah, I heard many of you right here. Very good. So this is going to be minus 2 over 6, which is ultimately going to be 1 minus 1/3, which is the 2/3 we were expecting. So again, I kind of spoiled that last class, but you can see we did get what we were expecting. So a little bit technical in terms of the algebraic simplification. It will take some time, especially if you aren't used to working with summations, but I don't think anything over here is overly convoluted, I would say, as you get the hang of it. Right now, it probably does feel a little intense, but any questions? Okay, so let me go ahead and get you set up on the next one, and then I'll give you a few moments to maybe try it. So let's look down here. Calculate the area under the curve over y equal to 2x for this interval 0 to 3. By the way, you don't even need calculus for this, to be honest, because if you think about this, let's go ahead and just sketch it. We would have 1, 2, 3. That's the interval that we're considering. And we can go ahead and graph this. Let me go ahead and try to keep this to this 1, 2, 3, 4, 5, 6. I'm trying to scale it appropriately. And this curve right here, y equal to 2x, has a y-intercept of 0. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. You're going to get this graph right here. Were to look at this, what shape, if I were to go ahead and consider shading underneath the curve, would we get? A triangle. So again, this graph extends on forever, but maybe just to clarify, what we're looking for is this area under the curve right here. You can figure this out. This is 6 by 3, so the area here is going to be 9, 1/2 base times height. So that, of course, is a geometric approach, and this is nice because we have a formula for it in terms of geometry, but obviously what the calculus allows us to do is if we have curves. So this is, of course, a straight line, so we have a formula. But let's confirm that we know how to work with this. This is going, so what we're going to do is we're going to have the area equal to the limit as n goes to infinity. And what we're going to need to do is sum from k equal 1 to n, where this n is going to be the size of our rectangles, or how many rectangles we have. So n is how many rectangles we have, and we're going to let the n go to infinity. But we have to be a little bit more careful with this, because the last time it was nice because we were between 0 and 1. Here, we're between 0 and 3, so we have to make a little adjustment for that. So it's really not too bad. What we're going to do is we're going to have to evaluate this function starting at the so that's going to 0 is where our rectangles start. So it's going to start at 0, which in this case is a. And then we're going to iterate through the rectangles. So k is going to go to n. So what we're going to need to do is we're going to have to figure out, ultimately, we're going to do 3 minus 0, where what we're looking at right here is this is b, this is a, and then we're going to divide this by n. So this is a more general setup that this right here is a. Then we have to get to 3, and we'll see it more obvious on the next step when we simplify it. And I'll go ahead and write the formula that I'm using above, and we'll take a moment to understand it. Then we have to multiply this by the width. The width of the rectangles are going to be 3 minus 0 divided by n. Again, notice this is going to be b, this is going to be a. So to simplify this, the limit as n goes to infinity, and we're going to sum from k equal 1 to n, so we're going to add up all of our rectangles. So this right here is just going to be 3k divided by n. And then we're multiplying this by 3 over n. And then, so, is everyone okay so far? Let's take a moment and just understand what we're looking at. Let's maybe look at the width right here. If you kind of consider if you have 3 rectangles, you would have like this first one right here, you would have this second one right here, and then you would have this third one right here. What is the width of each of those rectangles? 1. Notice if n is equal to 3, the width right here is going to be 1. So that's where this width is coming from. And then if you also think about this in terms of you let k equal from, that should have been 1 there, 1 to n, notice that to get the last rectangle, when k is n, you can see you're at f of 3, which is going to give you the height of the last rectangle. So it looks really messy, but it is pretty intuitive if you just think about it geometrically. This formula in general, I'm going to just write up here for reference. We'll use it a couple more times today just to get the hang of it. The limit as n goes to infinity. To find the area, where I consider that limit from k equal from 1 to n of f of a plus k times b minus a over n. So again, that is the input to the function that gives you the height. So this is going to basically be f of the some formula that we have. And then we're going to have the b minus a divided by n. This right here is delta x. Again, this is just our width of the rectangles. So hopefully that formula makes sense. Spend some time just kind of looking at it. And then ultimately, once you evaluate that summation, you go ahead and get the, take the limit, and you have the area under the curve. Okay, so any questions so far? All right, so the curve we're using right here is this y equal to 2x, so that's what we're going to need to do here. So let me do the next step, then I'm going to give you a moment to try it while I take attendance. So we're still going to consider the limit as n approaches infinity. We're going to sum from k equal 1 to n. And then this 3k plus n is going to be plugged into the function. So that's going to be 2 times 3k plus n. And then we still have 3 over n multiplied right there. So all that I did right here is just use the fact that y is equal to 2x. And then this is something that we should be able to evaluate through a series of algebraic steps. Any questions here? Let me give you a moment to see if you can work through it. I'll still talk through it just in case anyone needs to hear it. But I need a moment to take attendance, and I'll give you a moment to process everything we've done. I saw her walking to lunch and she didn't want to look at me. I'm like, she's probably not coming to class today. That's a telltale sign of like, it's like, if he doesn't see me, and if I don't see him, he doesn't see me. No, I hope everything's okay. Did you know if she's okay? Okay, just one of those surprises. Haley and Caleb, Sarah, Cadence, Weston, Grace, Alfred, Savannah, No Griffin, Say, Sarai, Christina, Marina, David, No Roxana, and Cora. Okay. All right, so we're almost done right here. I put up about 3 more steps. Was anyone able to maybe get to this point right here, or at least the summation was evaluated? Anyone? Emma's nodding. Everyone's kind of still processing, checking. All right, so how did we get here? Just to make sure, there was a lot of blank stares, like, not quite what I have, but so 3 times 3 is 9, times 2 gives us the 18. K is still in the numerator, n squared is still in the denominator. Remember our index that we moved through is k, so that means the 18n squared could be pulled out because those will be common in every term once we do the expansion. And then this right here is the sum of the first n positive integers. So we have a formula, thanks to an 8-year-old Gauss apparently, for that right there. And sometimes you just got to find the right way of looking at things. And that seems to be where that formula came from. But once you're here, we're pretty much done. I mean, however you want to simplify this, you may choose to do some simplification first. But ultimately, what we end up with here is an 18 squared plus 18n divided by a 2n squared. So when you take the limit, because everything is... we have matching degrees in the numerator and the denominator, is 18 over 2, or 9, which is what we expected based off our geometric knowledge. But this is consistent with the idea of letting the rectangles width go to 0, or let the let the number of rectangles go to infinity, however you're thinking about it. Does anyone have any follow-up questions? Did anyone get to 9 computationally? It's a little bit intense right there in the middle as you're getting the hang with sums, so take your time and practice. We'll do another 1 or 2 of these today just to help you all out. Sound like a plan? Okay. So before we go into 5.3, kind of some housekeeping in terms of things that as we continue, we want to keep in mind. I'm not going to spend a ton of time here because you really explore a lot of these ideas more in Calculus 2, but a couple assumptions that I want to kind of state that we've been making that's not necessarily true in the general case. So what we've been working with is something sometimes referred to as a Riemann sum. The idea of letting the rectangles get infinitely many rectangles or let the width of them shrink. So Riemann was a mathematician who formalized a lot of the ideas, so that's why it's sometimes referred to as a Riemann sum. A couple of things to note, in a Riemann sum, you don't necessarily have to have equal rectangles. So notice how some of these rectangles are larger than others. But again, you could always find the height of a rectangle by just considering some x value. So let me just maybe make a few notes about this idea. Notice that the rectangles may not be of equal width. And we'll explore this idea a little bit more. But with this idea, we get what is known as the Riemann sum. The Riemann sum is denoted with S sub p, and I'll tell us what p here is in a moment. It is the sum from k equal to 1 to n of f of ck, where c is just, again, circled up there in green. So you can see right here is ck. It is just going to be some x value. And then each rectangle will have its own width. So that's why we use delta x sub k, because each rectangle will have its own width. We're primarily going to work with the ones we've done where it's equal width, because if you let it go to infinity, it doesn't really matter that they're unequal. All that matters is that they're really thin rectangles. So that's one thing to note. So the next thing we should note is, what is P? P, I'll call it what it is. So it is referred to as a partition. Partition. P is going to basically be a bunch of x values that break up the interval. I'll define it formally on the next page. So it's like x sub 0. Here, let me color code this a little bit. Notice here that x sub 0 is the value of a. So x sub 0 is a. Then you have x sub 1, then x sub 2, and so on until you get x sub n, which is ultimately b right over here. So that is right there and right there. So it's what it's going to do is it partitions the interval based off of a bunch of x values. So those are n x values. Okay, and the other thing that we're explore more in 5.3 is, notice that the rectangles may be above or below below the x-axis. So we have to be careful because we've been talking about the area, but there is such a thing of kind of a cancellation of areas, which we want to be careful of if we actually want to know a particular characteristic about the area under the curve. More on that is in 5.3. So I just want to say a little bit more on partitions on the next page. Does anyone still need this page? Okay. So let's go down to the next page. Find the norm of the partition P, which is this right here. So let me go ahead and first define formally what a partition is. So a partition, here actually my writing is pretty atrocious as I try and do it in front of the class. So let me just copy it over, and then we'll go ahead and give you all a moment to write. Then we'll just do an example with it right here. So my writing's a little better when I do it out of class. So a partition P is a sequence of points in increasing order that divides the interval AB into subintervals. So you see we have a partition up above. And then the norm of a partition is denoted by double vertical lines surrounding whatever partition, and it is the largest of all subinterval widths. So we'll look at that visually down here below. So let me give everyone a moment to write that and process. And I'll just hang out up here. Do, 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 do. Y'all watch Jeopardy. Anyway, I'll let you write. Once you're good, just give me a thumbs up so I can see when the majority's there. Okay. Let me give it another 10, 15 seconds. What I would encourage you to do is see if you could actually decide what the norm is while we wait for maybe your peers just to finish processing. So here's the thoughts. Anyone need more time writing? Looks like everyone's good. Okay, so our partition is going to go from 0 to 2. So what we're going to look at here, so that's kind of the terminology. Let's go ahead and do the answer down here below. So our partition is going to go from 0 to 2. So let's put 0 here. Let's put 2 at our endpoint. I'm going to put about 1 here in the middle just for reference. Just to help us keep ourselves oriented, I'm going to also get 0.5, and let's kind of subdivide this one more to about 1.5. So again, our interval here is the first point in the partition, which is A, which is 0, and we're going to go from to 2. So let's go ahead and consider the partition here. So the first point is right here at 0, and then we're going to go to point 2, which is approximately right here. So what we're going to also, so that's point 2. We also then then we have the next one here at 0.6. Then we have it here at 1, then 1.5, then 2. So notice here we have 5 subintervals. So we have 5 subintervals, namely 0 to 0.2. Then we have 0.2 to 0.6. Then we have 0.6 to 1. Then we have 1 to 1.5. And then we have 1.5 to 2. So these are the widths. And again, this is one-dimensional. If you were thinking about the area, you would think these are the widths of our rectangles. So to figure out the width of these, it's just a matter of doing B minus A. So if we do B minus A, this is going to be 0.2. And actually, I don't want to do B minus A because that actually is already abusive in notation. Let's actually do x k plus 1 minus x sub k. It's because B minus A is used, so each of these are like really some, like this is x sub 0, this is x sub 1. So that's kind of what I'm doing right here is I'm just doing the endpoints of each subinterval. So I just didn't want to use A and B. So that's 0.4, this is 0.4, this is 0.5, and this is 0.5. The norm of the partition, denoted as bar bar B par bar. Wow, try and say that 5 times fast. bar, P, bar, nope. Bar, P, you got it. So bar, P, bar, or the norm of P is the largest of those subinterval widths, which is what in this case? Anyone? 0.5. So the norm of that partition is 0.5. So the more general approach, as I said, if we were to kind of extend and kind of look at Riemann's ideas a little bit more, so this is kind of maybe a closing thought on this lesson before we start 5.3, is generally what we do to control the width of the rectangle is let the limit, we consider the limit of the norm going to 0. So like I said, it's just a convenience we've been using, that they're all equal widths. If you let the norm go to 0, then the largest one is going to go to 0, so everything else is going to be forced to 0. More on that in Calc 2. We're going to use the general convenience of the equal widths in Calc 1. So the main thing we want to grab from this is what a partition is. It's just x values that divide up the interval we're looking, and then the norm is just the largest subinterval formed from the partition. Any questions on this page?